made a challenge before the talk that I would give the talk on the blackboard. But so since we are very pressed for time, I'm sorry I'm going to fail the challenge. I apologize for that. So we have very nice unity in our session today, because we see in every talk the role of symmetry. And we see also the importance of mixture models of different kinds. And then the EM algorithm comes up very often. But then we need to handle the complexity of the EM algorithm, maybe using online methods. And in any case, the question of model selection and Bayesian methods for model selection, knowing how many events we have or how many mixture components we have, is also an important question. We have very nice unity of the talks today. My talk is going to be complementary to what Yannick presented. So Yannick spoke about Gaussian distributions on Riemannian Gaussian distributions on symmetric spaces of negative curvature. And I'm going to clarify this by studying a specific example. So Riemannian Gaussian distributions are defined on symmetric spaces of negative curvature. And many spaces of covariance matrices, so spaces of real complex toplets, block toplets, covariance matrices, all belong to this category. And in order to, to clarify this definition, I want to study a special case, which is the case of quaternion covariance matrices, so positive definite quaternion matrices. So my aim is to further illustrate the Riemannian Gaussian distributions presented by Yannick. So the beginning idea of Riemannian Gaussian distributions is to work on a Riemannian homogeneous space. This is the quotient of a group of isometries G and a stabilizer group K. And to define a density with respect to invariant volume, which has this appearance similar to a normal distribution or Gaussian distribution, the key property, the most important thing to remember about this density is that the normalizing factor Z does not depend on X bar, it depends only on sigma. And this is because we are on a homogeneous space, so it's due to invariance. If you look at the normalizing constant as a function of X bar and sigma, there's translation invariance, so to speak, with respect to X bar that eliminates X bar. And as a result of this, we have the defining property of Riemannian Gaussian distributions, which is maximum likelihood is equivalent to the Paris center. So this is, if you want, the raison d'etre of Riemannian Gaussian distributions. Looking at the log likelihood functions, so because Z does not depend on X bar appears only in a center of mass least squares problem. So we have the correspondence between maximum likelihood and center of mass. An alternative definition would be as maximum entropy. So a Riemannian Gaussian distribution maximizes entropy among all distributions with hidden barycenter and dispersion. So you can understand it in either one of these two ways. This is nice, but in fact it's not useful if we don't know how to compute the function Z, because otherwise we can't estimate sigma. So to simplify Z, actually, there's two tricks. The first trick is to understand is when our Riemannian homogeneous space M is a product space, the function sigma decomposes into a product of functions, the function Z decomposes into a product of functions ZQ, each one of them corresponding to a factor in the Cartesian product of subspaces. And this is because the components of X actually are independent from each other. So if X has component X1 in M1, X2 in M2, these are independent from each other, and each one of them follows a Riemannian Gaussian distribution in the corresponding subspace. So this means we can break down Z of sigma in this way into lower dimensional integrals. The second trick is the structure theory of Riemannian symmetric spaces. So any Riemannian symmetric space of non-positive curvature is the product of something flat, like RP, and something which is called of non-compact type. It has strictly negative curvature, not only negative curvature. So M minus is the quotient of a non-compact semi-simple group and of a maximal compact group. And then actually our function Z is the product of a function ZRP for RP, which is just the normalizing factor of a standard normal distribution, and of another function which depends on the structure of these Lie groups here, but which is the multivariate Gaussian integral. So we know precisely how to compute the normalizing factor Z, thanks to one, breaking down the function Z using product spaces, and two, using the structure theory of Riemannian symmetric spaces. The formula here sometimes works even for reductive Lie groups, not only semi-simple Lie groups, but this is technical, but I will use it later on. And it's even possible to further break down Z of sigma when the space M minus is not irreducible. So this is something that Yannick mentioned also, the quality of irreducibility of symmetric spaces. So I want to look at a specific case of Riemannian symmetric spaces of negative curvature, which are cones. And to begin, among cones there are elementary cones, yes? So elementary cones are of the form R times M minus. Remember we had RP times M minus. Here P equals 1, right? So there are 5 kinds of elementary cones. First you have the cone of real covariance matrices in any dimension, the cone of complex covariance matrices in any dimension, the cone of quaternion covariance matrices in any dimension. Then you have an exceptional case, which is the cone of octonion covariance matrices of size 3 times 3. And then you have another infinite family, which is the Lorentz cone. Yes, so you have 4 infinite families and 1 exceptional case of elementary cones. For the first 4 cases, which are the cones of covariance matrices, we have a formula for Z of sigma using our integral formula from before, extended to reductive Lie groups as I mentioned. So here the formula depends on something called Rk. This is the rank of our space, and it's equal to n in the infinite cases or to 3 in the exceptional case. And then you have the m here, so m is equal to 1, 2, 4, or 8, according to whether you are looking at real, complex, quaternion, or octonion matrices. In any case, this is a Gaussian, this is like an integral with respect to a normal distribution, and it's very easy to evaluate and tabulate using Monte Carlo, and we have a specific Monte Carlo code for interpolating it and tabulating it in order to preserve its good properties, because this is a log convex function. It is a moment generating function, actually. So in the 5th case of the Lorentz cone, the normalizing factor looks like this. It can be calculated by hand because the integral is on R2 only 2 variables. And in general, any symmetric cone is just a direct product of elementary cones. So we have now developed Riemannian Gaussian distributions on any symmetric cone. I want to go into more details, yes? So now using this formula up here, it's possible to compute Z of sigma for the case of quaternion covariance matrices, which I said is going to be my case of study. But so it's possible to stop at this level, just implement this formula. But I want to go into more detail and describe the Riemannian geometry of the cone of quaternion covariance matrices. So quaternions are an associative norm division algebra, very famous, using these IGK, these 3 imaginary units. Quaternion matrices are very curious because you cannot compute with them in a usual way. Trace AB isn't equal to trace BA. AB transpose isn't equal to B transpose A transpose. But you have some rules that are always respected, the correct rules. For instance, AB conjugate transpose is equal to B conjugate transpose A conjugate transpose. Real part of the trace is commutative. So some rules hold, yes? Now we're interested in n times n quaternion matrices, which are symmetric, well, I should say Hermitian and positive definite in the sense indicated by the inequality, but the order is important because we have a non-commutative algebra, so the order of multiplication is important. This is a homogeneous space to the action of invertible quaternion matrices just by congruence transformations or affine transformations, and the stabilizer of identity is the set of matrices U such that U conjugate transpose equals identity. This is called the compact symplectic group, and it's a compact connected subgroup of GL and H. So now we have represented our space as a Riemannian homogeneous space. We can introduce the invariant Riemannian metric. In fact, it's only sufficient to introduce Lie algebra level computations. So we have the Lie algebra of our 2 groups. And if we introduce the SPN invariant scalar product on the Lie algebra of the quaternion linear group, then it's enough to pull this, to pull back the any 2 tangent vectors like UV, tangent at the point S, pull them back using A, and apply the Lie algebra scalar product to them, and we obtain, in red here, the Riemannian metric of the cone of quaternion covariance matrices. So it's real trace of S-1U, S-1V. Looks very much like the affine invariant metric of covariance matrices that we all know, but with a real part ahead of it. We also have an expression of the invariant volume, which involves the determinant. Now it's very complicated to define the determinant of a quaternion matrices because quaternions don't commute to each other. But here we can define it as the product of eigenvalues, yes? Now, even with this, we need to be careful because actually a quaternion matrix has an infinite number of eigenvalues, but we can choose eigenvalues that are real. For example, in the case of a Hermitian symmetric matrix, as is the case. So in order to carry out my integrals, I use polar coordinates. So any quaternion covariance matrix can be diagonalized. So we have K, which is, so to speak, quaternion unitary, means a special compact symplectic. And we have a positive diagonal matrix in the middle. So by performing some direct computations, the metric here, which is in red, in terms of polar coordinates, looks like this. So we have a part that's basically Euclidean in the eigenvalues, and the part that depends on the, I'm going to call it unitary part again, it's compact symplectic. And this is very useful because it tells us, if you look here, it's clear that in terms of R, this is Euclidean, so the distance from identity to any matrix S should be the sum of squares of the R of this matrix. And just by rotating this expression, to achieve any other couple of matrices, we obtain the general definition of Riemannian distance. And of course, the volume element, we just take the determinant of the metric and we have the volume element. It's the product of something for R here, and of an invariant form on this compact symplectic group. So this sine h to the power 4 is what we have originally from the structure theory of the symmetric space here. Here, I'm sorry, yeah, you have sin h to the power m, where m equals 4 in our case, and this is, we recovered it directly in this case. So now we can evaluate z of sigma. And so in polar coordinates, if S is equal to is diagonalized in polar coordinates, as I mentioned before, the square distance is the sum of Ri squared, sum of logs of eigenvalues. This doesn't depend on k, so k disappears from the integral. We have a multiple integral on Rn with a normal density inside it, and then some function which is a product of hyperbolic sines. So in general, as I said, we have a special Monte Carlo routine for doing this, but for n equals 2, we can take the integral by hand. And it's, so the normalizing function is this strange looking function here of sigma. So just to mention a coincidence, in fact, I mentioned there are 4 infinite classes of symmetric cones, elementary symmetric cones. Here we are looking at P2 of H, 2 times 2 quaternion covariance matrices. This is the same as lambda 6 Lorentz cone in 6 dimensions because of a certain way of writing these matrices. It's very simple, in fact. So as I mentioned before, we are able to introduce Riemannian Gaussian distributions on all symmetric cones. Yeah. In particular, we took a special case of quaternion covariance matrices. So if I may, I don't know if I have much time left. Yeah? Oh, wait. I think I still have, I have 1 minute. Until, yeah, see, it's 1 minute. So in real world, so I'm going to go back to density estimation now. In real world situations, of course, we never know that our data comes from a Riemannian Gaussian distribution. This is our artificial thing to imagine. However, any real world continuous density can be approximated by a finite mixture. So this is the importance of mixtures. that I mentioned at the beginning. So the EM algorithm is a standard choice. How does it work? In fact, it's like the EM algorithm for estimating mixtures of Gaussian distributions that you know, except when you're estimating the barycenter of each mixture component, this amounts to computing a weighted Riemannian barycenter. And then you have just a nonlinear, simple nonlinear transformation for the dispersion parameters. So it's a fairly straightforward generalization of the EM algorithm, but we need to pay attention to the Riemannian aspect. So at one time we compute a weighted Riemannian barycenter. This is possible because we know how to compute geodesics, so we can compute Riemannian barycenters in a standard way by following Riemannian gradient descent. So as Yannick mentioned, in practice, for large volumes of data, this has many drawbacks, and this is why we are very interested in research on stochastic EM and online EM, because these avoid storing huge volumes of data, and also they avoid being trapped in local minima and saddle points. So an important message, I guess, for me is that EM is a good theoretical place to start, but practice has shown we need to look at more advanced and robust versions of EM to deal with big data, basically. So thank you for your attention.
So do you have questions?
If I understand the definition of the Riemannian Gaussian distribution correctly, then I think it's defined on more general classes of manifolds. So when you say introduced, do you mean, is that particularly for the normalizing constant to be independent?
Yeah, I see your question. Well, it's possible to write this expression down. That's always possible, and as long as it integrates to one, it's a probability density, yes? But what we want specifically is maximum likelihood is equivalent to barycenter. And that does not happen unless Z is independent of X bar. And Z independent of X bar is basically a byproduct of Riemannian homogeneity. Yeah.
So here you have, so here you have a single scalar dispersion. Right?
Yes, good question.
So what happens when you get covariances of covariances?
Sure. Thank you. That's a very good question. So I think later on Emmanuel will have a talk about this question. So thank you for asking this actually. So in fact, my framework, or the framework presented here, is not extensible to the case where we have a covariance matrix, because we wouldn't know how to compute the normalizing constant very easily. There's a thing that happens in these integrals. Let's think of just a usual real covariance matrix. So it's diagonalizable. You have eigenvectors and you have eigenvalues. What we exploit is that the function we're integrating, the squared Riemannian distance or its exponential, depends only on the eigenvalues. And so when we integrate over the eigenvectors and they disappear in a nice way, right? Now, if we have a covariance matrix in there, it's possible, it's not always the case, but it's quite possible that the function we integrate will depend on the eigenvectors of the matrix. And then we will have a more complicated integration to carry out. I'm sorry, yeah, I
Was it an answer?
Yeah.
If you stay until like, the next presentation.
So I asked also because I wonder, so if I remember correctly, if I remember correctly, then Aaron Schwartzman has sort of similar work, but under a different metric, where he simply just derives the Jacobian at the exponential map.
Sure. Well, this is what I do also.
But I think he does it under the affine invariant metric, and there sort of you can get covariances of covariances to get the full. I just wonder, like, if you are aware of the links.
No, I'm not aware of the work that you're mentioning. However, well, I'm also doing it under an affine invariant metric. So, but in any case, I want to say something. please don't think of this distribution as being an isotropic distribution, because it depends on something which is highly nonlinear and isotropic, which is the Riemannian distance. Yes. Yeah, so I think to give you the honest answer, this framework that I presented does not accommodate the covariance matrix.
Okay, I think we have to go to the next presentation. So let's thank the speaker again.